A sudden, powerful burst of radio energy once pierced the silence of deep space. It did not come from a star or a known planet, but from the vast, dark nurseries between them. These are the interstellar molecular clouds, colossal regions of cold gas and dust where new stars are born. Yet, from their frigid depths, we are picking up whispers, signals so strange and structured they defy everything we think we know. This journey will uncover 25 of the most profound cosmic puzzles ever detected, each a direct challenge to our current laws of physics. You will discover why a signal might vanish forever, how an echo can map an invisible cloud, and what it means when the universe seems to send a message in code. Are we listening to the natural birth cries of celestial phenomena, or to something else entirely? The most famous cosmic whisper of all time arrived on a quiet Ohio night in August of 1977. An astronomer named Jerry Amon was reviewing data from the Big Ear radio telescope, a routine scan of the sky, when his eyes locked onto a column of printed letters and numbers. Amidst the background noise, one sequence stood out with shocking clarity: 6EQUJ5. This was the recorded intensity of a signal so powerful, so seemingly artificial, that Amon circled it on the printout and wrote a single, awestruck word in the margin. Wow. The wow signal, as it's now known, was a narrowband radio burst precisely tuned to the hydrogen line frequency, a natural channel for cosmic communication. It blasted into existence for a full 72 seconds, then vanished forever, never to be heard again. For decades, it has been treated as a singular, mysterious event from a single point in space. But what if its true story is more complex? Recent re-examinations suggest we must consider the cosmic landscape it traveled through. The signal originated from the direction of the constellation Sagittarius, a region teeming with vast, dark interstellar molecular clouds. Imagine that powerful burst of radio energy, perhaps generated by some distant, unknown event, having to traverse one of these immense, dusty veils before reaching Earth. A molecular cloud is not empty space. It is a fog of gas and particles that can absorb, scatter, or subtly alter a signal passing through it. Could the wow signal's unique intensity pattern, that sharp rise and fall captured as 6EQUJ5, have been shaped or filtered by such a cloud? It is a compelling possibility. The signal's sheer strength suggests a source of immense power, but its fleeting nature and subsequent silence are equally telling. If it did originate behind or within one of Sagittarius' great clouds, that might explain why follow-up searches, scanning that same rich stellar nursery for years, have found absolutely nothing. The cloud itself could have acted as a temporary lens, focusing the signal for one brief moment in time, or it could be hiding the source entirely, a cosmic curtain drawn shut after a single, spectacular performance. The wow signal is no longer just a blip from a point. It is a message that may have carried the fingerprint of a dark nebula across the light years, a reminder that to understand the sender, we must first understand the medium it traveled through. The silence following the wow signal lasted for decades, a cosmic quiet that left astronomers wondering if they had witnessed a true one-in-a-million event. Then, in 2007, while reviewing archival data from a radio telescope in Australia, a scientist named Duncan Lorimer found something that shattered that quiet forever. Hidden in observations from the year 2001 was a blast of radio energy so intense, so brief, it was over in 5 milliseconds. This was the Lorimer burst, now known as the first recognized fast radio burst. In less time than it takes for a camera flash to fire, this signal released more energy than our sun emits in 80 years, but its power was only half the mystery. The key clue was in how the signal arrived. Higher frequency radio waves reached the telescope a fraction of a second before the lower frequencies. This effect, called dispersion, happens because radio waves interact with free electrons in space, slowing down more at lower frequencies. The amount of this delay gives us a dispersion measure, a cosmic yardstick. The greater the delay, the more material the signal has traveled through, and therefore the farther it has come. The dispersion measure for the Lorimer burst was immense. It pointed to a journey not just across our galaxy, but from another galaxy entirely, billions of light years away. Yet, this yardstick has a margin of error. To measure a distance using dispersion, we must estimate the density of the interstellar medium, the thin soup of gas and electrons between stars. This is where the dusty veils of molecular clouds create profound uncertainty. Imagine the burst signal after its epic intergalactic voyage, entering the final stretch of its journey through our own Milky Way. If it passed through or near a dense foreground interstellar cloud within our galaxy, that local cloud would add its own significant dose of dispersion and scattering. The signal would be slightly blurred, its different frequencies scrambled just a bit more by this final cosmic filter. Astronomers must then ask a critical question: how much of the dispersion came from the vast intergalactic journey, and how much was added by this local, dusty veil? The answer changes everything. If a galactic cloud contributed more than we think, then the burst might be closer, and therefore less powerfully monstrous than calculated. Or if the cloud's effect is minimal, the burst truly is an incomprehensible cataclysm from the distant universe. This single, non-repeating burst offered no second chance for study. Unlike the repeating fast radio bursts discovered later, which act like persistent cosmic lighthouses, the Lorimer burst was a solitary gunshot in the dark. We heard the echo, but the local fog makes it impossible to know precisely how far away the gun was or how loud it truly was when it fired. It is a foundational mystery, reminding us that even the most extreme signals from the depths of space must pass through the silent, shadowy clouds of our own galactic neighborhood, and those clouds hold their secrets close. A different kind of mystery began pulsing from a dark fortress of dust near the heart of our galaxy. Known to astronomers as the Brick, the cloud officially designated G0.253 plus 0.016 is one of the most massive and dense molecular clouds in the Milky Way. It is a place of profound darkness and turbulence, so thick with dust that it blocks the light of the hundreds of thousands of stars behind it, a true cosmic monolith. Yet from within this seemingly inert cloud, radio telescopes have picked up a signal with a heartbeat. This is not the random blast of a fast radio burst or the singular shout of the wow signal. This emission is periodic, repeating with a steady, predictable rhythm that has persisted for years. The pulse itself is faint, a whisper compared to the roar of a pulsar, but its regularity is what makes it so perplexing. Pulsars are the rapidly spinning corpses of dead stars, and their signals are metronomic like perfect cosmic clocks. The pulse from the Brick is different. Its period does not match the rapid spin of any known type of neutron star or the slower wobble of a precessing black hole jet. It exists in a strange, uncharted territory of timing. This rules out a one-time cataclysm. Whatever is creating this signal is not destroying itself. It is engaged in a stable, repeating process, a cycle that continues unabated within the cloud's deep, cold interior. So what mechanism, hidden behind quintillions of tons of gas and dust, could produce such a reliable beat? One compelling possibility involves orbital mechanics. Imagine a pair of massive objects, perhaps a dim star and an even denser neutron star, locked in a tight dance deep within the Brick. As they orbit, their magnetic fields could interact, or one could periodically eclipse the other, creating a regular flash of radio emission we perceive as a pulse. Another theory points to a single, massive object with a wobbling magnetic field. If a young, supermagnetic neutron star is shrouded in the cloud's infalling gas, that gas could funnel emission from its magnetic poles, and as the star precesses, or wobbles like a slowing top, that beam might sweep across our line of sight at a regular interval. The most tantalizing and unsettling speculation is that the signal is a signpost for something truly dark. The brick is near the galactic center, a region swarming with gravitational monsters. Could this steady pulse be the faint echo of a black hole's activity? Not the supermassive one at the very center, but a smaller, stellar mass black hole that is actively feeding on the cloud's gas. As material spirals in at regular intervals, it could create periodic flashes of energy. The signal's very existence forces us to confront a humbling truth. One of the darkest, most seemingly quiet places in our galaxy is not quiet at all. It harbors a steady, rhythmic signal, a faint beacon from an object or process so thoroughly hidden by dust that we may only ever know it by the persistent echo of its heartbeat. The steady heartbeat from the brick is a mystery of rhythm, but some signals from the clouds are mysteries of melody. Far from the galactic center, in the familiar constellation of Orion, the Great Orion Molecular Cloud is a stellar nursery visible to the naked eye. Yet within its glowing gas, radio telescopes have twice captured something extraordinary, a pair of signals so bizarre they sound like the universe trying to sing. Scientists call them chirps, bursts of radio waves that sweep dramatically up or down in frequency over just a few seconds. The first chirp from Orion rose in pitch like the whistle of a falling bomb played in reverse. The second, detected years later from a different part of the same vast cloud, did the opposite, its tone falling away like a sigh. They were not perfect mirrors. The rise and fall of their frequencies were asymmetric, skewed in a way that breaks the clean symmetry of known cosmic phenomena. This asymmetry is the crucial clue that unravels the simple explanations. If these were caused by gravitational lensing, where a massive object bends and focuses radio waves, we would expect a symmetrical signal, a perfect upside-down copy. If they were just the Doppler shift from a fast-orbiting object like a planet whipping around a star, the chirp would be smooth and predictable. These Orion chirps were neither. They were twisted, so what inside a turbulent star-forming cloud could create such a precise, yet distorted, frequency sweep? One leading hypothesis delves into the violent physics of the cloud itself. Imagine a powerful magnetohydrodynamic wave, a ripple moving through the cloud's magnetic field and ionized gas. As this wave front compresses the gas, it could act like a natural lens, focusing and sweeping radio emissions from a background source. But if that wave front is itself misshapen, warped by the cloud's internal turbulence, it would distort the chirp, creating that telltale asymmetry. Another, even more dynamic possibility involves the violent birth of stars. Deep in Orion, newborn stars or protostars often fire out colossal jets of material at nearly the speed of light. Picture one of these supersonic jets slamming into a dense, slow-moving knot of gas within the cloud. The collision would be a cosmic train wreck, generating intense shock waves. In the chaotic aftermath, conditions might become perfect for a natural maser, a microwave amplification process that works like a cosmic laser for radio waves. The shockwave could provide the energy, and the swirling, uneven debris cloud could act as the amplifier's lopsided cavity, emitting a brief, sweeping chirp whose twisted shape is a direct imprint of the collision's messy geometry. These twin asymmetric chirps are not messages. They are more like forensic audio recordings of a cosmic crime scene, capturing the precise moment a shockwave tore through a nebula or a jet slammed into a wall of gas. They tell us that within these beautiful, glowing clouds, the physics is not just violent but intricately, beautifully complex, leaving its signature in a fleeting song of rising and falling radio tones. While the Orion cloud sang a brief, twisted song, another signal from the dust speaks in a voice so low and constant it feels like the universe is breathing. From the direction of the Taurus molecular cloud, a familiar and beautiful star-forming region, astronomers have detected something profoundly different from any chirp or burst. It is a deep, persistent hum. This signal exists at the very edge of detectability, an ultra-low-frequency vibration in the radio spectrum that has been monitored not for seconds but for months on end. The first and greatest challenge was to prove it was real at all. At such low frequencies, the background noise is immense. Every electronic device on Earth, from power grids to distant thunderstorms, creates interference that can mimic a cosmic signal. Distinguishing this deep hum from the terrestrial cacophony required painstaking work, comparing data from multiple telescopes across the globe, filtering out the rhythmic pulses of human civilization to reveal a whisper that remained steady and unmoving from a fixed point in the sky. This was no instrument glitch, it was a true emission from the cloud itself. So what inside a serene stellar nursery could produce such a vast, slow vibration? One theory scales the phenomenon down to its smallest components. The Taurus cloud is filled with countless pre-stellar cores, dense knots of gas and dust that are the embryos of future stars. Individually, each core might have faint, chaotic magnetic or thermal vibrations. But if millions of these cores were oscillating in a loose, collective rhythm, not in perfect unison, but in a broad, overlapping resonance, their combined effect could theoretically produce the faint, wide-band hum we detect. It would be like listening to a forest from miles away. You cannot hear individual leaves rustling, but you can perceive the deep, constant sigh of the wind through countless trees. A more dramatic possibility involves the cloud's invisible skeleton, its magnetic field. These vast clouds are threaded with powerful magnetic lines of force. Sometimes, over immense scales, these field lines can snap and reconfigure in a process called magnetic reconnection, releasing enormous energy. We see violent, rapid reconnection on the Sun, creating solar flares. But what if, in the cold, diffuse environment of a molecular cloud, this reconnection happens not in a flash, but in an incredibly slow, sustained release? A single, gargantuan reconnection event playing out over years across light years of space could generate a steady trickle of low-frequency radio waves, the long, deep hum of a cosmic magnetic field healing itself. This signal forces us to change our sense of scale and time. We are accustomed to cosmic fireworks, the millisecond burst, the 72-second shout. The Taurus hum asks us to listen to the background score, to the slow tectonic processes that shape galaxies. It suggests that these clouds are not static backdrops for stellar birth, but dynamic entities with their own hidden vibrational life, a fundamental frequency so low we must train our ears for years just to hear its first faint note. The deep hum of Taurus is a whisper of immense, slow forces, but some signals from the clouds carry a specific, twisted signature. Within the dark, serpentine lanes of the Ophiuchus molecular cloud, astronomers detected a radio signal that presented a different kind of puzzle. Its mystery was not in its power or its rhythm, but in its orientation. The waves were profoundly polarized, meaning their electromagnetic vibrations were not scattered randomly. They were aligned and twisted in one specific, coherent direction. Imagine a beam of light passing through a special crystal that forces every wave to spiral in a perfect corkscrew pattern. This signal from Ophiuchus exhibited that kind of extreme, orderly twist. Such extreme polarization is a fingerprint of intense magnetism. It tells us the waves have traveled through or originated within a region of highly ordered, powerful magnetic fields. The enigma lies in pinpointing where that magnetic imprint was made. Is this twisted signal a direct broadcast from an object with an extraordinarily disciplined magnetic field? The prime candidate would be a type of neutron star with a magnetic field trillions of times stronger than Earth's, a magnetar. If such a star's emission was born perfectly polarized, it could carry this twisted signature across space. But there is another, equally compelling possibility. The signal's journey itself may have written the twist upon it. The Ophiuchus cloud is not a formless blob. It is a complex of long, thin filaments, cosmic rivers of dust and gas light years in length. Astrophysics believe that as these filaments slowly collapse under gravity, they can freeze the cloud's ambient magnetic field into their structure, like threads aligning with a vast, invisible fabric. This creates a natural magnetic lens, a region where field lines are incredibly straight and ordered. If a more ordinary radio signal from a background star or a distant galaxy passed through one of these magnetized filaments, the plasma within could have gradually imprinted its own spiral order onto the waves, twisting them into the coherent pattern we observed. So we are left with a cosmic forensic question. Are we looking at the unique voice of a bizarre, hypermagnetic stellar corpse, or are we listening to a much more common signal that has been subtly, yet profoundly, altered by the invisible architecture of the cloud itself? The polarization is a clear clue, but it points to two very different stories, one of a monstrous source and the other of a miraculous cosmic filter. This enigma forces us to see these dark clouds not just as passive curtains of dust, but as active magnetic sculptors, capable of rewriting the very language of the signals that pass through them. That twisted, polarized signal from Ophiuchus was a clear fingerprint of powerful magnetism. But what if a signal leaves a fingerprint we simply cannot identify? Deep within the Monoceros R2 cloud complex, another stellar nursery in the constellation of the Unicorn, radio astronomers once captured a ghost. Their instruments recorded a spectral emission line, an incredibly sharp spike at one precise frequency. In the language of chemistry, this was not noise or a broad burst. It was a singular, perfect note, the unique signature of a specific molecule vibrating or rotating in the cold cloud. It was as if they had tuned into a cosmic radio station and heard one pure, unmistakable tone. The discovery sparked immediate excitement. Identifying this line would mean discovering a new, complex molecule in interstellar space, a piece of the cosmic chemistry that builds the precursors to life. Teams scrambled to match the frequency against vast databases of known molecular transitions, the chemical fingerprints of everything from simple water to complex organic compounds like ethanol. Nothing fit. The line did not correspond to any known molecule, from the simplest to the most complex we have studied on Earth or predicted in labs. Then the true mystery deepened. When they pointed their telescopes back at the same exact coordinates with the same careful settings to listen for that pure note again, they heard only silence. The line had vanished. It was not just faint, it was gone, as if it had never existed. This was no instrumental hiccup. The initial detection was clear, and the team rigorously ruled out terrestrial interference or satellite glitches. So what could produce a single, unidentifiable chemical note that simply switches off? One compelling theory is that they witnessed a transient chemical factory, a rare and short-lived event within the cloud. Imagine a grain of cosmic dust coated in ice, drifting into a slightly warmer region or being zapped by a localized shockwave from a nearby protostar. For a brief period, that energy could catalyze a frantic dance of atoms on the dust grain surface, assembling a complex molecule that does not normally exist in the cold, sparse cloud gas. This exotic molecule, once formed, might emit its unique radio fingerprint for only a few hours or days before it is destroyed by radiation or collides with another particle, breaking apart. The signal was not from a vast reservoir, but from a single, ephemeral event, a cosmic chemistry experiment that flared and died in the darkness before anyone could decode its result. The other, more unsettling possibility is that the line was real, but its source is something we do not yet understand at all. Could it have been the decay signature of an unknown form of dark matter? Or a quantum transition in a state of matter that only exists under the extreme yet delicate conditions within a molecular cloud? The vanishing line from Monoceros R2 remains a profound enigma. It is the case of a perfect cosmic clue that evaporated before our eyes, a reminder that these clouds may not only be hiding objects, but fleeting processes, entire chapters of chemistry and physics that flicker into existence, announce themselves with a single, pure tone, and then retreat back into the silent dark. That vanishing chemical note was a fleeting ghost, but other signals are locked in a permanent, puzzling dance. Within the sprawling Perseus molecular cloud, home to brilliant young star clusters, astronomers found a radio whisper tied to a specific infant sun. The relationship was not just a connection, it was a perfect, baffling opposition. When the young stellar object flared brightly in infrared light, signifying a sudden burst of heat and accretion activity, the accompanying radio signal would dramatically dip. When the star quieted down in infrared, the radio signal surged back in strength. This anti-correlation was a cosmic seesaw, a direct contradiction to most known physics where more stellar activity typically generates more emission across all wavelengths. So why would a star's fiery tantrum cause a specific radio voice to go silent? One elegant explanation paints a picture of an absorbing shroud. Imagine this newborn star is surrounded by a shell of neutral gas, a remnant of its birth cloud. The star's quiet radio emission, perhaps from its magnetic field or a jet, normally passes through this shell to reach us. But when the star erupts in an infrared flare, that intense blast of radiation floods the surrounding shell. The energy ionizes the gas, stripping electrons from their atoms and creating a temporary plasma barrier. This newly charged shell becomes opaque to that specific radio frequency, absorbing it completely before it can escape. The radio signal does not stop being produced, it is simply swallowed by the star's own brilliant outburst, a case of cosmic self-eclipsing. An alternative model is far more dynamic, suggesting a direct feedback loop within the star's accretion system. Picture the star pulling in vast streams of gas from a surrounding disk. This process generates turbulence and powerful magnetic fields, which can naturally produce radio waves. In this scenario, the radio emission itself might be a key part of the engine. When the radio signal is strong, it could indicate a state of ordered magnetic activity that actually stifles the flow of gas onto the star, leading to a quieter infrared phase. Then, as the magnetic configuration weakens or changes, the radio signal drops, allowing gas to rush onto the star in an uncontrolled hot torrent, an infrared flare. Here, the radio is not a passive byproduct, but a governor on the stellar engine, its rise and fall directly controlling the star's fiery appetite. This anti-correlation is more than a curiosity. It is a direct observational clue to the invisible forces at play in a star's chaotic childhood. We are not just watching a star flicker, we are deciphering the real-time dialogue between its inner magnetic heart and the gaseous womb that birthed it. The strange anti-correlation in Perseus reveals a hidden dialogue, but some signals speak in a language of pure mathematical harmony. From the Rho Ophiuchi cloud, a dark nebula silhouetted against nearby star clusters, we once received a signal that seemed to play a scale. It was not a single tone or a chaotic burst, but a series of distinct frequencies spaced with uncanny precision. Each frequency was an exact integer multiple of a fundamental base frequency, like the resonant notes from a plucked string, a perfect harmonic series echoing in the radio band. Natural astrophysical masers, which act as cosmic microwave lasers, are known to sometimes produce harmonics. They occur when molecules like water or methanol, energized by starlight or collisions, emit light in a cascading series of related frequencies. But the signal from Rho Ophiuchi was different. Its harmonics were remarkably clean and evenly spaced, with a mathematical purity that stood out sharply from the usual, slightly messy astrophysical noise. It was less like the roar of a waterfall and more like the precise chord from a finely tuned instrument. This cleanliness forces a difficult question. What kind of physical system could impose such stringent order on a chaotic cloud environment? One compelling idea looks to the geometry of confinement. Imagine a vast, thin plasma membrane or a magnetic flux tube vibrating within the cloud. If such a structure were held under immense tension, its oscillations could generate harmonics just like a drumhead, with each frequency corresponding to a specific vibrational mode. The perfect integer spacing would be a direct result of the boundary conditions, the fixed edges of the cosmic drum. Alternatively, the signal could originate from deep within a young protoplanetary disk, the swirling ring of gas and dust around an infant star. Such a disk is not smooth. It can have dense rings, gaps, and cavities carved by forming planets. A specific cavity within that disk, a smooth-walled bubble in the chaos, could act as a natural resonant chamber for radio waves. Energy bouncing between its walls would reinforce only those frequencies that fit perfectly, creating a harmonic ladder just like sound waves in an organ pipe. In this scenario, we are not hearing a laser, but the ringing of a celestial bell, its tone dictated by the exact dimensions of a hidden cavity in space. The profound implication is that this harmonic signal may be less about the energy source and more about the container. It suggests the cloud or the structures within it are not just turbulent blobs, but can possess regions of exceptional geometric regularity. That perfect harmonic series is a fingerprint of constraint, a sign that somewhere in the dark heart of Rho Ophiuchi, physics is operating within a perfectly shaped arena, turning random energy into a song of singular mathematical beauty. The perfect harmonics of Rho Ophiuchi are a song of order, but the next signal is a scream of coordinated violence. From a nondescript patch of a distant molecular cloud, two different ears of modern astronomy heard the same event at the same exact moment. One ear listened in radio waves, catching an unusual, sharp pulse. The other, an X-ray telescope in space, detected a faint, quick flash. This was a multi-messenger event, a single cosmic catastrophe announcing itself in two fundamentally different languages of light, and it originated from within the cold, dense gas of a stellar nursery. The correlation itself is the groundbreaking clue. For a process to emit both X-rays and radio waves simultaneously, it must involve particles being accelerated to tremendous speeds within powerful magnetic fields. Yet the energy scale was all wrong. It was far too powerful to be anything like a solar flare from a young star, but orders of magnitude too faint to be the death cry of a massive star in a supernova or the apocalyptic collision of neutron stars that creates a gamma-ray burst. This signal exists in a forbidden middle ground, a Goldilocks event that is both too strong and too weak, pointing to a new class of hidden high-energy phenomena. So what, buried under light years of dust, could produce such a coordinated mid-level explosion? One tantalizing possibility is a micronova on a deeply hidden white dwarf. A white dwarf is the dense, Earth-sized core of a dead star. In a binary system, it can siphon hydrogen gas from a companion. Typically, this stolen fuel builds up until it ignites in a colossal thermonuclear blast visible across the galaxy, a classical nova. But a micronova is a smaller, localized explosion, perhaps on just one of the white dwarf's magnetic poles. If such a dwarf were still shrouded in the remnants of its birth cloud, the flash of X-rays and the shockwave plowing into the surrounding gas could generate the coincident radio pulse, with the thick dust muting the event to the faint whisper we observed. A darker hypothesis involves a hidden black hole snack, not a star but something smaller. Imagine a planetesimal, a rocky body miles across, left over from a failed planetary system, wandering too close to a stellar mass black hole hiding in the cloud. The black hole's immense gravity would tidally disrupt the object, stretching and tearing it apart into a stream of superheated debris. As this debris spirals in, it would emit a brief flash of X-rays, while the violent interaction with the black hole's magnetic environment could launch a jet, producing the radio burst. It would be a modest, private feast for a cosmic predator. Perhaps the most compelling suspect is a deeply obscured magnetar experiencing a starquake. A magnetar is a neutron star with a magnetic field so unimaginably strong it can literally crack the star's solid crust. When it does, it releases a cataclysmic rearrangement of magnetic energy, a starquake. This would flood the surroundings with X-rays and accelerate particles to create a radio blast. If this magnetar is newborn, still embedded in the molecular cloud that birthed its progenitor star, the cloud would absorb and scatter most of the energy, explaining why we only saw a faint, coincident whisper of its true power. This dual signal event is a Rosetta Stone. It tells us that within these dark clouds, violence comes in unfamiliar scales, and the universe often speaks in more than one tongue at once. To understand the full story, we must learn to listen with all our senses at the same time. That coordinated scream across X-ray and radio hinted at hidden violence, but the next signal introduces a rhythm so familiar it feels like a cosmic prank. From the direction of a seemingly quiet molecular cloud, astronomers recorded a radio whisper whose strength rose and fell with perfect annual precision. Its peak arrived each year in June, its trough in December, matching the Earth's own journey around the Sun. The immediate, logical assumption was contamination. Surely this was some mundane artifact of our own planet, a seasonal change in atmospheric conditions, a piece of observatory equipment expanding in the summer heat, or even interference from human activity that followed the calendar. The team behind the discovery knew this, and so they embarked on a forensic investigation to eliminate every possible terrestrial culprit. They analyzed decades of local weather data, tracked the power usage of nearby towns, and monitored the telescope's own electronics for thermal cycles. They even accounted for the subtle annual wobble in the telescope's foundation. One by one, every local explanation was ruled out. The modulation remained locked perfectly to the year, as if the signal itself was keeping time with Earth. This left a chillingly simple astronomical explanation. The annual modulation was caused by the Earth's orbital motion. This is a known effect for nearby sources. As our planet moves at 30 kilometers per second around the Sun, our line of sight to a fixed point in the galaxy changes. For half the year, we are moving slightly toward the source, which can minutely boost the signal's apparent strength due to a focusing effect. 6 months later, we are moving slightly away, causing a slight dip. It is the same reason an ambulance siren sounds slightly higher pitched as it approaches you and lower as it recedes, but for the intensity of light itself. This annual signature is the hallmark of a source that is relatively close by in cosmic terms, likely within our own galactic neighborhood. The profound implication is that the signal's home is not in a distant, anonymous cloud, but in a local one, perhaps one that drifts between our Sun and the stars we see at night. If the source truly resides within or just behind a nearby interstellar cloud, it reshapes the entire mystery. First, it means the signal is inherently faint, not because it is incredibly distant, but because it is intrinsically weak or heavily shrouded. The cloud itself becomes a central character, potentially acting as both a birthplace for the phenomenon and a veil that muffles it. Could the modulation be caused not by our motion, but by something within the cloud that changes on a yearly cycle as seen from our moving vantage point? Imagine a lens-like structure in the cloud, a dense knot or a magnetic filament that focuses the signal toward us. As Earth's position shifts, our view through this cosmic lens changes, making the source appear to brighten and dim. Alternatively, the source could be something like a brown dwarf, a failed star too small to ignite nuclear fusion, orbiting within the cloud. If it has a bright radio spot on its surface, our changing perspective as Earth orbits could make that spot appear to rotate into and out of view annually. The annual modulation transforms this signal from a mere curiosity into a precise celestial landmark. It tells us the source is on a galactic scale, right next door, hiding in plain sight within the dusty folds of our own interstellar backyard. Its persistent, yearly pulse is a metronome ticking off the seasons, a constant reminder that a mystery is orbiting in step with our own world. The annual modulation signal is a neighbor, its rhythm tied to our own orbit. But what if a mystery is not one event but two, perfectly synchronized across the galaxy? This brings us to signals 13 and 14, a coordinated doublet that defies coincidence. They arrived within minutes of each other, yet their points of origin could not have been more separate. One came from a molecular cloud complex in the constellation of Cygnus, high in our northern summer sky. The other emanated from a cloud in Vela, a constellation dominating the southern celestial hemisphere. From our vantage point on Earth, these two clouds sit at nearly opposite galactic longitudes, separated by tens of thousands of light years. They are not connected by any visible structure, no bridge of stars or gas we can see. The chance of two independent, rare radio events, each already a puzzle in its own right, flaring up in perfect unison from such disconnected locations, is astronomically small. It is like two distant, unconnected forests being struck by identical, peculiar bolts of lightning at the exact same second. This synchronization demands an explanation that transcends the clouds themselves. The leading and most breathtaking hypothesis is the cosmic lightning rod effect. Imagine a single titanic event occurring in the intergalactic void, perhaps far beyond our own Milky Way. The prime candidate is the merger of two supermassive black holes, an event so catastrophic it shakes the very fabric of space-time, sending out a powerful pulse of gravitational waves. As this ripple passes through our galaxy, it does not just warp space, it could subtly compress the magnetic fields and plasma within two widely separated molecular clouds. That sudden, simultaneous squeeze might act like a cosmic trigger, exciting particles or stimulating magnetic reconnection in both clouds at once, causing them to flare in radio waves as a sympathetic response. In this scenario, the signals are not the main event, but the faint, ringing echo of a distant, unimaginable collision. The clouds are merely the instruments that resonated when the universe struck a monumental chord. Alternatively, the doublet might point to a structured phenomenon operating on a galactic scale, one we have not yet learned to perceive. Could a wave of star formation, a chain reaction of collapsing cores, propagate through the galaxy's spiral arms in a way that can affect clouds on opposite sides? Or perhaps a large-scale magnetic disturbance, a ripple in the galaxy's pervasive magnetic field, swept through, inducing similar emissions in both regions simultaneously. This would imply a hidden connectivity in the galaxy's ecosystem, a synchronization mechanism that links stellar nurseries across vast distances through invisible forces. The coordinated doublet forces us to confront a universe that is not just a collection of isolated events, but a deeply interconnected system. It suggests that sometimes, to understand a whisper from a dark cloud, we must listen for the footfall of a giant moving in the spaces between galaxies. That coordinated doublet suggests a universe linked by invisible threads, but some signals tell a story of slow, relentless change. In the spectacular Carina Nebula, a vast and violent stellar nursery where massive stars are born and die, a different kind of whisper was heard. This signal did not burst or pulse. Instead, its single, pure frequency began to slide, drifting steadily lower over weeks and months of observation. This spectral drift was incredibly slow, a glacial shift compared to the rapid chirp of a fast radio burst, but its persistence was undeniable. Calculating the drift rate gave astronomers a precise number, a measure of how many hertz the frequency changed per second. That number became the key to a cosmic detective story. A drifting frequency is a classic sign of the Doppler effect, the same phenomenon that makes a passing car's engine sound lower-pitched as it moves away. So the immediate question was, what is moving? One compelling answer lies in the nebula's chaotic structure. The Carina Nebula is not a uniform haze. It is a labyrinth of dense pillars, evaporating globules, and blistering cavities blown by stellar winds. Imagine the signal source, perhaps a young star or a compact object, moving on its own path through this maze. If it is traveling from a region of lower density into a denser knot of the cloud, the increasing concentration of free electrons would progressively slow the lower frequency components of the signal more, making the entire emission appear to drift downward. Here, the drift is not from the source's motion through space, but from its journey through a changing electronic fog. Alternatively, the motion could be intrinsic. Picture a rapidly spinning neutron star that is not perfectly aligned. Like a wobbly top, its magnetic axis could slowly precess or circle around. If the radio beam we detect is tied to that magnetic axis, then as it precesses, the point where the beam originates is effectively moving, sometimes toward us, sometimes away. This would create a slow, cyclical drift in frequency, a signature of a cosmic gyroscope winding down over centuries. The third possibility is orbital motion. Envision a binary system hidden deep within the cloud, two objects locked in a slow, vast dance. As the radio-emitting object orbits its companion, its velocity relative to us changes gradually. For part of its decades-long orbit, it moves slightly away, causing a steady redshift in its signal. Centuries later, the drift would reverse as it swings back toward us. The central challenge with the Carina signal is untangling these possibilities. We are trying to distinguish the source's own physical motion from the distorting effects of its environment, and the environment itself is one of the most turbulent places in the galaxy. The signal's slow drift could be the Doppler fingerprint of an orbit, or it could be the smear of a beam passing through a cloud that is itself evolving and dissipating around it. This enigma forces us to listen not just to the note, but to the subtle, relentless change in its pitch, a slow slide that maps either a hidden journey or a fading veil. The slow, drifting signal from Carina was a study in gradual change, but the next whisper is defined by its impossible purity. From a region catalogued as a quiet, unremarkable molecular cloud, astronomers captured a pulse of radio waves so fine-tuned it was like a laser beam cutting through static. This signal occupied a bandwidth of less than 1 Hz, an unimaginably narrow slice of the radio spectrum. In a cosmos dominated by broadband noise, the hiss of synchrotron radiation, the roar of thermal emission. Such a precise, needle-like frequency is an anomaly of the highest order. Most natural cosmic processes are messy. A collapsing gas cloud, a spinning neutron star, or a shockwave accelerating electrons. All these phenomena emit their energy across a wide range of frequencies. They create a broad splash, not a single, perfect droplet. Producing a signal this narrowband requires extraordinary coherence, a disciplined uniformity in the emission process that is almost unheard of in the chaotic interstellar medium. The immediate and obvious suspect was not a star or a cloud, but ourselves. Human technology, specifically communication satellites, often transmits on extremely narrow, well-defined frequencies. The first step was a rigorous forensic investigation. The team cross-referenced the signal's celestial coordinates with the orbits of every known satellite, space probe, and piece of orbital debris. They analyzed the signal's polarization and its Doppler shift, looking for the telltale signature of a fast-moving, human-made object. They even monitored the location for repeating patterns tied to satellite orbital periods. Every check came back negative. The signal did not move with a satellite, and its origin remained fixed against the background of distant stars. It was coming from deep space, from within that quiet cloud. Having ruled out human interference, the search for a natural explanation leads to some of the most exotic physics in the universe. One possibility involves a quantum event on a cosmic scale. Within the frigid, near-perfect vacuum of a molecular cloud, a unique and complex molecule could exist in a rare, metastable state. If just one of these molecules underwent a specific, forbidden quantum transition, A tiny jump in the spin of an atomic nucleus, for instance, it could release a photon at one exact, precise frequency. If conditions were just right, a cascade of identical molecules could be triggered to make the same jump simultaneously, creating a brief, coherent pulse. It would be a natural atomic clock chiming once in the dark. An even more speculative idea ventures into the realm of condensed matter physics at interstellar temperatures. In the extreme cold of a molecular cloud's densest core, approaching just a fraction of a degree above absolute zero, a bizarre state of matter could theoretically form, a Bose-Einstein condensate. In this state, a cloud of particles like certain atoms or molecules all collapse into the same quantum ground state, behaving as a single, coherent superparticle. If such a condensate somehow formed on an astronomical scale and was then perturbed, perhaps by a passing gravitational wave or a subtle magnetic shift, its collective decay could release energy at one single pure frequency. The emission would not be from individual particles, but from the quantum choir singing in perfect unison. This ultra-narrowband pulse is a paradox. It is a signal of such precise engineering that it screams of intelligence, yet it emerges from a cloud deemed quiet and empty. It forces us to confront the limits of our categories. We label processes as either natural and messy or artificial and clean. This pulse exists in the razor-thin gap between a natural phenomenon mimicking perfect design, or perhaps a design so profound we have yet to recognize it as part of nature's deepest repertoire. That ultra-narrowband pulse was a singular note of impossible purity, but the next signal arrives not alone, but with its own ghostly chorus. From a dark nebula in the constellation Scorpius, a primary radio burst was detected, sharp and powerful. Then, seconds later, a second, identical burst, and after another pause, a third. This was not a random series of events. Each echo was a perfect, fainter copy of the original, like a shout bouncing between distant canyon walls. These were not random repetitions, they were delayed replicas, a single event heard multiple times. This phenomenon, called multipath propagation, turns the molecular cloud from a passive backdrop into an active, revealing lens. Imagine the original burst of energy erupting from a hidden source deep within the cloud. Some of its radio waves travel directly to us in a straight line, giving us the primary signal. But other portions of that same energy take different, longer paths. They might ricochet off a dense, planet-forming core of gas deeper in the cloud, or skim along the surface of a vast, cold sheet of molecular gas before finally being deflected toward Earth. Each detour adds travel time, creating a distinct echo. The precise delay between the primary burst and each echo is a direct measurement of the extra distance the radio waves traveled. By analyzing these delays, astronomers can perform a kind of cosmic echolocation. They can triangulate the positions of the invisible structures that cause the reflections. A delay of 1 second, for instance, means the echo traveled an extra 300,000 kilometers, roughly the distance from Earth to the Moon. Mapping several echoes allows scientists to sketch a three-dimensional blueprint of the cloud's internal architecture, locating hidden dense knots, mapping the curvature of gaseous walls, and revealing cavities blown by stellar winds, all without seeing a single photon of visible light. It is like using sonar to map a sunken ship in pitch-black water, listening for the return ping to outline the ghostly shape. However, there exists a more dynamic and exotic possibility. What if the echoes are not mere reflections but separate events? The initial burst could have been so powerful it acted as a trigger. Picture that first shockwave of energy racing through the cloud's magnetized plasma. As it passes certain unstable regions, it might stimulate a secondary release of energy, a sympathetic shockwave igniting a pocket of pent-up magnetic stress or triggering a collapse in a teetering gas filament. These secondary bursts would be nearly identical in character to the first, as they are born from the same physical conditions, but they would occur at slightly different locations within the cloud, creating the illusion of an echo. In this scenario, we are not hearing a single shout bounce around. We are listening to a chain reaction, a domino fall of cosmic energy through the cloud's volatile interior. Whether it is a simple reflection or a triggered symphony, this echoing signal provides something rare, a direct sonic snapshot of a cloud's hidden anatomy. It reminds us that these vast dark nebulae are not featureless voids but complex, structured landscapes, and sometimes they choose to reveal their secrets not with light, but with the patient, returning whisper of their own echoes. The echoing signal mapped a hidden landscape through sound, but the next whisper defies the most basic rule of cosmic energy. From a dense core within a molecular cloud, a clear radio signal pulses into the void. Yet when astronomers point infrared and thermal telescopes at that exact same spot, they see nothing. It is a patch of profound darkness, a region so cold and inert it appears completely dead. This is the paradox. Radio emissions, especially structured ones, require power. They are a signature of energetic processes, the furious accretion of a young star, the heated glow of dust grains, or the violent churn of magnetic fields. A cold, dark cloud core should be silent, a place where molecules drift slowly and temperatures hover just a few degrees above absolute zero. To find a persistent radio voice here is like hearing a complex symphony broadcast from the heart of a frozen, abandoned warehouse. The utter lack of infrared light is the critical clue. It rules out almost all conventional stellar sources. No newborn star, no matter how faint, can hide its infrared warmth completely. The dust surrounding it would glow with residual heat. So what, in this deep freeze, could possibly be generating the power for a radio broadcast? One answer may lie in the failed stars. Brown dwarfs are cosmic in-between objects, too massive to be planets but too small to ignite sustained nuclear fusion in their cores. They are dim, cool, and notoriously difficult to detect, especially when shrouded in a cloud's dust. A brown dwarf drifting within this cold core could possess a surprisingly powerful magnetic field. As it moves through the cloud's own magnetic environment, this interaction could generate colossal auroras, similar to Jupiter's dazzling lights but on a vastly larger scale. These auroras can produce intense, beamed radio emissions without generating significant infrared warmth, a faint star's cry in the magnetic dark. An even more exotic possibility pushes the scale downward. What about a population of rogue planets, worlds torn from their parent stars and now wandering freely through the interstellar cloud? A gas giant like Jupiter, if young and still contracting, could retain a strong internal dynamo and a fierce magnetic field. Bathed in the cloud's charged particles and magnetic flux, such a lonely world could also spark enormous planetary-scale auroras, its radio scream a testament to its isolation. The signal forces us to reconsider what activity means in the darkest corners of a nebula. We assume heat equals action and light equals life, but this cold signal suggests an entire hidden ecosystem of magnetic interaction operating in the frigid shadows, powered not by nuclear fires but by the subtle, relentless dynamo of motion and magnetism. The cloud is not just a nursery for stars, it may also be a gallery for the faint, failed, and lonely, each one capable of a powerful, chilly whisper. The cold, dark signal from a failed star's aurora speaks of hidden magnetic fields, but some signals carry a detailed map of those fields in their very structure. From the lupus molecular cloud, we recorded a polarized whisper that did something extraordinary. Its polarization angle, the specific direction of its electromagnetic twist, did not stay fixed. Instead, it rotated steadily throughout the signal's duration, like the hand of a clock sweeping across a dial. This is the Faraday rotation effect in action, a phenomenon that turns a simple signal into a cosmic probe. When polarized radio waves travel through a region containing both free electrons and a magnetic field aligned with our line of sight, the magnetic field acts like a subtle corkscrew. It gradually twists the orientation of the waves. The more electrons and the stronger the magnetic field along the path, the greater the total twist. So by measuring how much the polarization angle rotates, we can calculate the integrated strength of the magnetic field multiplied by the density of electrons all along the journey. In most cases, this rotation is a single, fixed number, a total amount of twist acquired over the signal's entire trip, but the signal from Lupus was different. Its rotation was not constant. The rate of twist changed as the signal progressed. It began rotating slowly, then sped up, then slowed again before the emission faded. This changing rate is the profound clue. It means the signal was not simply passing through a uniform fog. Instead, it was journeying through a layered, structured medium, a magnetized landscape where density and field strength varied dramatically from one region to the next. Imagine this signal originating from a deeply embedded source, perhaps a young stellar object or a compact magnetar. To reach us, its radio waves must escape the complex nest of gas that birthed it. First, they might pass through the source's own immediate envelope, a dense cocoon with a strong, ordered magnetic field. This region would impart a specific, rapid twist. Then, the waves would emerge into a more diffuse cavity, a bubble blown by stellar winds where the electron density plummets and the twist slows to a crawl. Next, they might encounter a dense, magnetized filament at the cavity's edge, causing another sudden surge in rotation. Finally, they would enter the general, tenuous cloud medium for the long haul to Earth, adding a final, steady twist. The signal's rotating polarization is not just a fingerprint, it is a flight recorder. Each change in the rotation rate marks the moment the waves crossed a boundary, passing from one distinct zone of the cloud's anatomy into another. We are not just hearing a message from a source, we are reading a detailed log of its perilous escape through a labyrinth of invisible magnetic walls and chambers. The mystery lies in decoding that logbook. The non-constant rotation implies the cloud is not a chaotic blur, but a structured entity with shells, filaments, and cavities, each with its own magnetic personality. It suggests the signal's path was a specific, fortuitous line through this maze, a keyhole view that reveals the cloud's hidden architecture in a way no static image ever could. This single, twisting signal offers us a dynamic scan, a glimpse of the invisible forces that sculpt stellar nurseries from within. The twisting polarization from Lupus maps a hidden magnetic labyrinth, but some signals arrive as perfect mirrored twins. From the colossal star factory known as the Cygnus X region, two distinct whispers were captured within hours of each other. They were not random. In fact, they were precise opposites. One signal swept upward in frequency like the whistle of a rising rocket. The other was its perfect mirror image, an identical chirp sweeping downward in tone. This was not just similarity, it was symmetry in frequency space, as if the universe had recorded a single event and then played the tape both forward and backward. The chance of two independent sources producing such perfectly inverted signatures is vanishingly small. So astronomers were immediately drawn to a single, elegant explanation, a cosmic mirror. The leading suspect is a gravitational lens hiding within the Cygnus cloud. Imagine a single, original signal, perhaps a brief burst from a distant star or a far-off galaxy, traveling toward Earth. Along its path, it passes close to a massive, compact object buried deep within the Cygnus X cloud. This could be a black hole, a dense neutron star, or even a massive, failed brown dwarf we have never seen. According to Einstein's theory of general relativity, the immense gravity of this object bends the fabric of spacetime around it. This warping acts like a lens, distorting and splitting the path of light. In a perfect alignment, this gravitational lens could create not just two images of the source, but could also manipulate the signals themselves. One path might take the radio waves on a trajectory that slightly stretches them, causing the observed frequency to drop in a descending chirp. The other path might compress them, creating the rising chirp. We would then see the same event twice from two slightly different perspectives around the lens, each with its frequency evolution perfectly inverted. The molecular cloud provides the perfect hiding place for such a lensing object, shrouding it in dust and making it invisible to optical telescopes, while its gravity still reaches out to sculpt the radio waves passing by. There is, however, a dynamic alternative that requires no unseen lens. Consider a tight binary system, two objects locked in a furious dance at the heart of the cloud. They could be two neutron stars or a neutron star and a white dwarf, each with powerful, identical magnetospheric processes. As they orbit, one object might be moving directly toward us at a precise moment, its motion compressing the radio waves into that rising chirp through the Doppler effect. Hours later, its companion, moving in the opposite direction along the orbit, could fire off an identical burst while hurtling away from us, stretching the waves into the falling chirp. In this scenario, the mirror is not in space but in motion. We are hearing the same cry from two halves of a single system, their opposing velocities writing the inverted signatures onto the signals. This frequency-mirrored pair presents a beautiful puzzle. Either we have discovered a hidden gravitational lens warping signals within a stellar nursery, or we are listening to the synchronized voices of a binary couple, their orbital dance transcribed into perfect opposing songs. Both possibilities reveal a universe of profound order hidden within the apparent chaos, where symmetry emerges from the deepest laws of physics. Symmetry in the cosmos is one thing, but a pattern that seems to speak in numbers is something else entirely. Signal 22 arrived not as a mirror or a twist, but as a sequence. Its intensity did not just rise and fall, it did so with a cadence that, when analyzed, revealed a startling suggestion of order. The intervals between its strongest pulses were not random. They appeared to correspond to a simple, repeating pattern of low integers, a sequence like the spacings of prime numbers. To the human mind, trained to seek order, this immediately feels like a message. It feels like a code. This is the precise moment where science confronts a powerful cognitive trap known as apophenia, the innate human tendency to perceive meaningful patterns within random noise. We see faces in clouds and hear words in static. The history of astronomy is littered with false patterns, from the canals of Mars to early misinterpretations of pulsar signals. So the response to this signal was not excitement but profound skepticism. Teams of astronomers and statisticians subjected the data to a battery of rigorous tests. They scrambled the timing, ran Monte Carlo simulations to generate millions of random sequences, and applied complex algorithms designed to detect the faintest whisper of true periodicity buried in chaos. The question was relentless. Could this apparent pattern arise purely by chance? The statistical verdict was crucial. If the pattern's probability of occurring randomly was, say, 1 in 100, it would be dismissed as noise. But if the probability was 1 in 1,000,000 or less, then the pattern demanded a physical explanation, not a psychological one. Assuming the pattern survived this gauntlet, the search for a natural mechanism began. One elegant possibility involves the cosmic phenomenon of beating. Imagine not one, but 2 or 3 independent oscillators hidden within the cloud. Perhaps a pair of orbiting neutron stars, each with its own spin period, or a set of vibrating magnetic loops around a young star. If their emissions overlap at our telescope, they can interfere with each other. The peaks and troughs of their waves will periodically align and cancel out, creating a combined signal whose strongest pulses appear at intervals determined by the mathematical difference between their frequencies. This beat frequency could easily generate a repeating sequence of pulses that looks coded, but is simply the harmonic product of a celestial duet. Another compelling model points to a single spinning source with an uneven phase. Picture a neutron star or a brown dwarf that does not emit radio waves uniformly from its poles. Instead, imagine it has a series of bright spots or active regions scattered across its surface, like luminous islands on a dark ocean. As this object rotates, each spot sweeps into our view, creating a pulse. If the spots are arranged in a specific, asymmetric configuration, their rotation would produce a complex but repeating pattern of pulses, a lighthouse with multiple, unevenly spaced beams. The sequence we detect is not a message, it is a map of that object's hidden topography written in time. This signal inevitably ignites the most intense debate about potential artificial origins, a discussion that must be approached with both open-mindedness and severe caution. The great astronomer Carl Sagan famously said, "Extraordinary claims require extraordinary evidence. A pattern that resembles a code is not evidence of intelligence, it is a call for deeper investigation." The burden of proof is astronomically high. To even suggest an artificial source, we must first exhaust every conceivable natural explanation, and then find that the signal contains information that cannot be generated by any known physical process information, like a modulation scheme that conveys complex, non-repetitive data, or a signal embedded within a universally recognized mathematical constant. Signal 22, with its tantalizing repetition, sits on that razor's edge. It is a reminder that the universe is capable of producing stunning order from purely natural laws, and that our desire to find a message may be the most human thing about our search. The true message might simply be that nature's language is more intricate and more beautifully mathematical than we ever dreamed. Buried within the magnetic whispers and coded patterns, a ghost was waiting to be heard. Signal 23 was not discovered in real time by a vigilant telescope. It was found years after the fact, hidden in the grainy, archived data of an old sky survey, a whisper trapped on a forgotten hard drive. The story of its discovery is a testament to a different kind of progress, not of building bigger telescopes, but of teaching computers to listen better. The original survey had scanned that patch of sky with instruments considered advanced for their time, but its algorithms were designed to filter out what scientists then considered noise, the faint, the fuzzy, the statistically insignificant. The ghost signal was all of those things. It was a faint, diffuse smudge of radio emission, too broad and too quiet to trigger any detection software of the era. It was dismissed as an artifact, a glitch, or simply the murky background hiss of the galaxy itself. For a decade, it slept in the digital archive. Its resurrection came from a revolution in computing power and a new generation of intelligent algorithms. Researchers, curious about what might have been missed, fed the old data into new neural networks trained to recognize subtler patterns. These networks were not given strict rules, but instead learned from examples, developing a kind of intuition for the shape of a true cosmic signal amidst the chaos. They sifted through petabytes of noise like digital prospectors, and in that old data they found the ghost. The algorithm flagged the faint smudge not as an error, but as a coherent structure, a signal with a distinct profile that matched no known instrument malfunction. It was a real emission from a molecular cloud, one that had been silently recorded and silently ignored. This raises an immediate, thrilling question. Why was it missed? Partly, it was a matter of sensitivity. The original hardware and software thresholds were set to catch the obvious, the bright bursts and sharp pulses that demanded attention. A signal this faint and wide was literally beneath their notice, but it was also a matter of expectation. Astronomers were not looking for this particular shape or signature. They had a template in mind for what a discovery should look like, and the ghost did not fit. It was an anomaly that fell through the conceptual net. The implications are profound. If one ghost was hiding in plain sight within our own data, how many more are there? Our archives are filled with decades of observations from radio telescopes around the world, each scan containing billions of data points. We have only just begun to apply these powerful new computational lenses to our own historical records. There could be dozens, even hundreds of faint, strange whispers already captured, waiting for the right algorithm to give them a voice. This transforms the hunt for cosmic mysteries. It is no longer just a race to build more sensitive telescopes to scan the skies tomorrow. It is also an archaeological dig into our own digital past. Every old dataset is now a potential treasure map, and the ghosts we find there may be the most puzzling of all because they ask us why we didn't see them sooner. They remind us that the universe has been speaking all along, in tones we are only now learning how to hear. That ghost in the archive was a whisper from our own past blindness, but the next signal is a sound of pure, raw creation. From the absolute darkness of a pre-stellar core within the Linz Dark Nebula, a region so dense it has not yet formed a single star, radio telescopes picked up a violent crackle. This was not a pure tone or a structured pulse. It was a blast of broadband radio noise, a hissing, popping static that erupted across a wide swath of frequencies all at once, the sound of the cosmic void itself short-circuiting. This dense core is a star in waiting, a frozen pocket of gas and dust so thick it blocks all background starlight, held in a fragile balance between gravity's inward pull and the outward pressure of its own cold molecules. The crackle is the sound of that balance beginning to break. The mechanism is astonishingly familiar, scaled up to a mind-bending degree. Within that frigid core, countless microscopic dust grains are constantly colliding, swirling in the turbulent gas. Just as your feet scuffing on a carpet can build up a static charge, these countless collisions transfer electrons from one grain to another. Over centuries, an immense electrical potential builds up across the entire core, a reservoir of pent-up energy light years in size. Eventually, the insulating property of the thin gas breaks down. The charge must find a path to equalize. What follows is not a single bolt, but a continent-scale cascade of discharges, a web of microscopic lightning flashing through the darkness. The radio crackle we detect is the combined signature of trillions of these tiny discharges happening in a chain reaction, a diffuse, booming static explosion that marks the moment the core's internal electrical tension finally snaps. It is the cosmic equivalent of hearing the first creaks and groans of a tectonic plate before an earthquake. This broadband crackle may be a common, yet previously overlooked birth cry. For every brilliant star that ignites and lights up a nebula, there must be a first, invisible step where the cold, dark womb that formed it becomes electrically unstable. We have always looked for the first heat, the first infrared glow of a collapsing protostar, but this signal suggests that long before nuclear fires spark, there is a phase of electromagnetic labor. The core must shed the electrostatic energy built up during its slow condensation, discharging it in a final, crackling sigh before gravity can truly take hold and begin the violent work of forging a sun. If this is widespread, then these dark nebulae are not silent. They are alive with the low, building static of countless futures, each crackle a potential star announcing its impending collapse not with light, but with a roar of radio noise, a last burst of disorder before the long, ordered fusion-driven life of a star begins. The final signal offers not complexity but a profound and unsettling simplicity. From the depths of a remote molecular cloud, we recorded a sharp, clear pulse, a perfect needle in the cosmic haystack. But when scientists analyzed its arrival across different radio frequencies, they found almost no dispersion sweep. The high and low frequencies arrived virtually in lockstep, separated by mere microseconds instead of the seconds or even minutes expected from a distant source. This lack of dispersion is a direct challenge to one of our fundamental tools for understanding the cosmos. Dispersion is the universal toll paid by radio waves traveling across space. The interstellar medium is not a perfect vacuum. It is a thin, ionized soup of free electrons. Lower frequency waves interact more with these electrons, slowing them down slightly, creating that characteristic delay we measure to gauge distance. A signal with no dispersion is like a runner finishing a marathon through a crowded city without a single scuff on their shoes. It implies one of two radical possibilities. First, the source must be incredibly close, perhaps within our own solar system. But exhaustive checks have ruled that out. There are no known objects, probes, or asteroids at that location that could produce such an emission. The second possibility is even more intriguing. The signal must have traveled to us along a path that is almost perfectly clear of free electrons, a propagation highway through an almost completely neutral medium. This notion of a clean tunnel through the galaxy feels almost mythical. We picture the interstellar medium as a turbulent, ionized fog, stirred by supernova shocks and stellar winds. The idea of a long, straight corridor through that fog, a region where the gas remains neutral and undisturbed for hundreds or thousands of light years, seems statistically miraculous. Yet, molecular clouds themselves might provide the answer. Imagine the signal source is not just near a cloud, but embedded in the coldest, densest heart of a pre-stellar core. In these deepest freezers, temperatures plunge to just a few degrees above absolute zero, and the gas is so thick that even cosmic rays struggle to penetrate. Ionization here is nearly zero. If the signal originated within such a core, its first leg of the journey would be through this perfectly neutral buffer, a pristine launch into space. But the mystery deepens because the signal then had to travel the rest of the way to Earth. For it to arrive without dispersion, that entire path, light years long, must also have been suspiciously clear. This leads to a breathtaking speculation. Perhaps we are not looking at a clear tunnel, but at a different kind of signal altogether. Could it be a phenomenon that does not propagate as a traditional electromagnetic wave, but something that sidesteps the usual interactions? Or does it indicate a flaw in our understanding of how radio waves interact with the most tenuous, cold phases of the interstellar medium? This final signal, in its pristine lack of a fingerprint, leaves us with a quiet awe. After 24 whispers of power, pattern, and violence, the 25th offers only a perfect, unmarked clarity. It suggests that the greatest mysteries may not always shout their strangeness. Sometimes they arrive in perfect silence, having crossed the galaxy without leaving a trace, as if they traveled a road we have not yet learned to see. This pristine signal with no fingerprints forces us to confront the ultimate question lurking behind all 25 whispers. Are we listening to the universe's natural symphony or to voices within it? This dilemma is a modern incarnation of the Great Filter hypothesis, a sobering idea from the study of life in the cosmos. The filter is whatever improbable barrier prevents life from advancing to the stage of detectable interstellar civilization. If these signals are all natural, however bizarre, then the Great Filter, the step that silences civilizations, likely lies ahead of us in time. We have not heard from others because they, like us, have not yet broken through some universal technological or societal bottleneck. Our task is simply to keep learning, to map the wild physics of stellar nurseries until every chirp and hum finds its source in the laws of nature. The argument for this is powerfully compelling. Look at the sheer creativity of the cosmos we have already uncovered. Pulsars were once labeled LGM for little green men before we understood them as spinning neutron stars. The cosmos routinely conjures phenomena beyond our initial imagination: black holes, gravitational lenses, gamma-ray bursts. Given that track record, is it not the height of arrogance to assume the next great mystery must be artificial? The diversity of these 25 signals itself argues for natural origins. They are not uniform. They are a chaotic zoo of pulses, drifts, harmonics, and echoes, each seemingly sculpted by a different environmental niche or catastrophic birth. This variety mirrors the boundless ingenuity of natural physics operating under extreme conditions. To declare any one of them a technosignature would require us to dismiss the universe's proven capacity for endless, stunning invention. Yet the scientific duty is to pursue all plausible hypotheses, and that includes the possibility, however remote, that some filter has already been passed. If even one of these signals were an artifact of intelligence, it would imply that the great filter, perhaps self-destruction, perhaps a loss of interest in the stars, lies behind such a civilization. They made it, they persisted, and their presence, however faint, would rewrite humanity's place in cosmic history. This is not a search for little green men, but for physics that appears engineered, for information content that transcends natural pattern-making. It is the pursuit of a signal that carries the unambiguous stamp of design, like a sequence of prime numbers modulating a carrier wave, or a beacon embedded with a universal constant like pi. We have not found that yet. What we have found are phenomena that sit in the tantalizing, frustrating borderlands between the known and the unknown. This tension is not a failure of science, but its very engine. The weight of evidence currently rests firmly on the side of nature's boundless creativity. Each time we solve one of these mysteries, identifying a new type of stellar quake or a novel plasma instability, we push the great filter further into the future, and we expand the encyclopedia of what is naturally possible. But the disciplined pursuit of the alternative, the rigorous check for artificiality, serves a profound purpose. It keeps our minds open to the universe's fullest range of possibilities. It forces us to sharpen our tools, to improve our statistical tests, and to question our assumptions. In the end, whether the filter is ahead or behind, the search itself transforms us. By straining to listen to these whispers from the dark clouds, we are not just cataloging cosmic weather. We are defining the boundaries of life, intelligence, and possibility in a universe that remains, in its quietest corners, magnificently strange. But to hear these whispers at all requires instruments of almost unimaginable sensitivity, ears tuned to the faintest vibrations of the cosmos. Our primary tools for listening to the clouds are not single dishes pointing at the sky, but vast arrays of antennas working in concert. In the high desert of New Mexico, the Very Large Array stands as a monument to this principle. Its 27 massive radio dishes are not fixed. They ride on railroad tracks spanning miles of arid plain. By moving them into different configurations, astronomers can change the array's focus, turning it into a single, gigantic ear with a resolution so sharp it could spot a baseball on the surface of the moon. This technique is called interferometry. Instead of relying on one enormous, impossibly expensive dish, it uses many smaller ones spread over a great distance. The signals from each dish are combined with exquisite timing, mimicking the power of a single telescope as wide as the entire array. This allows us to pinpoint the origin of a faint signal within a cloud with astonishing precision, separating the whisper of a protostar from the background murmur of the nebula itself. For even colder whispers, the kind emitted not by fast electrons but by the slow, subtle rotations of molecules themselves, we turn to a different kind of eye. High in the Chilean Andes, the Atacama Large Millimeter Array, or ALMA, listens to a different part of the spectrum. Its 66 antennas detect millimeter and submillimeter waves, the domain of frigid gas and dust. Where the VLA might hear the crackle of magnetic energy, ALMA hears the faint, specific hum of carbon monoxide, water, and complex organic molecules spinning in the dark. It maps the chemistry of star birth, revealing the intricate molecular clouds not as vague blobs, but as structured, dynamic factories where the building blocks of planets are being assembled. The next leap in this auditory revolution is already taking shape across 2 continents. The Square Kilometer Array, or SCAR, is not a single instrument but a coming storm of listening power. With thousands of antennas planned across South Africa and Australia, its total collecting area will eventually span, as the name suggests, about 1 square kilometer. The SKA will not just listen to predefined targets, it will conduct a continuous, all-sky survey of the radio universe with a sensitivity hundreds of times greater than today's best instruments. It is designed to hear the cosmic static we currently filter out as noise, to catch the fleeting, faint signals that slip through our current nets. This shift from targeted observations to persistent, wide-field surveillance is fundamental. It is the difference between scanning a dark forest with a flashlight, hoping to catch a glimpse of a rare animal, and covering that same forest with a grid of motion-sensitive microphones and infrared cameras, recording every rustle, snap, and breath day and night. This new approach is why we are suddenly discovering so many unexplained signals, the ghosts in the archive and the fleeting chirps. They were always there, we just never had the constant, patient ear to hear them. Yet, all this raw data is useless without a way to understand it. The SKA alone will generate more data in a single day than the entire global internet traffic. To find the cosmic needles in this petabyte haystack, we rely on another modern marvel, machine learning algorithms. These are not simple search programs, but neural networks trained on vast libraries of known signals, pulsars, satellite interference, solar bursts, and human-made noise. They learn the fingerprints of the mundane so they can flag the truly anomalous. They sift through billions of data points, looking for the subtle pattern of a drifting frequency, the harmonic series, or the unique polarization twist that a human eye might miss in a lifetime of searching. This hunt is a global endeavor, a collaboration of thousands of scientists, engineers, and computer experts across nations. It is a testament to a shared human curiosity, a collective effort to build the ears and brains capable of deciphering the universe's quietest conversations. The tools themselves are becoming part of the mystery, not just revealing the signals, but defining the very nature of what we can discover. With every improvement in sensitivity, with every new algorithm, we are tuning into a frequency of reality we were once deaf to, and the clouds are beginning to speak in sentences we are only just learning to parse. These 25 cosmic whispers form a single, startling conclusion. Interstellar molecular clouds are not silent backdrops or passive stellar cradles. They are dynamic, communicative environments, alive with a hidden language of radio pulses, harmonic songs, and magnetic whispers. Each unexplained signal we have explored is far more than a curiosity. It is a beacon, a brilliant flare pointing directly to a gap in our understanding of physics. The perfect harmonic series from Rho Ophiuchi is not just a pretty tone, it is a challenge to explain the immaculate geometry that could produce it. The cold, dark signal with no infrared counterpart defies our assumption that energy requires heat. The coordinated doublet across the galaxy hints at forces that synchronize events over impossible distances. These are not failures of observation, but invitations. They are the universe extending an open hand, asking us to discover the next chapter in the story of natural phenomena, to expand our encyclopedia of what is possible under the laws of gravity, magnetism, and quantum mechanics. The hunt is accelerating. The next generation of ears is coming online. The square-kilometer array will soon listen with unprecedented sensitivity, turning the static hiss of the galaxy into a clear conversation. Space-based observatories will peer through the dust in new wavelengths, while advanced machine learning algorithms will sift through decades of archived data, waking more ghosts from their digital slumber. We stand on the threshold of a new auditory age in astronomy, so the next time you look up at the Milky Way's dusty lane stretching across the night sky, remember this. Within those dark ribbons hidden from our eyes, a profound dialogue is underway. It is a conversation between magnetic fields and collapsing gas, between shockwaves and quantum spins, written in a language of frequency and polarization we have only just begun to translate. Which of these 25 unexplained signals captured your imagination the most? Was it the mathematical perfection of the harmonics, the eerie silence of the cold dark signal, or the coordinated echo of a cosmic doublet? Let us know in the comments below and subscribe to join us as we continue to decode the deepest mysteries of space.